Great. Welcome to the first session of the last day of this wonderful conference. Today we're going to hear from Ursula Martin from the Department of Computer Science at the University of Oxford. Mathematical process, crowdsourcing, and things.
Okay, so this isn't actually the advertised talk, this is a different talk. I apologise, first of all, that I seem to be very afflicted by jet lag, but I didn't make it any better by staying awake far too much of the night following the British election. And of course now I'm really sad because, yeah, we need a new science. We clearly need a new science of polling, because all the polls, right up to the wire, were saying it was going to be neck and neck, Tory and Labour, and that's completely wrong. Tories completely in control. Leader of Labour has resigned, leader of the other minor parties have resigned. And the only really happy people are the Scottish Nationalist Party, who took 56 out of 59 seats in Scotland. I live in Scotland, I have a house in Scotland, I used to work in Scotland. Who took 50 seats out of 69 with a manifesto that should have been the Labour manifesto, because it was actually far more inclusive, far more anti-austerity, which is why they completely wiped the Labour Party out in Scotland. However, it means I'm a bit leery on this. Right, so this is a talk about a project I have going at the moment. And what I'm doing is thinking about how mathematics is done, or mathematical practice in the jargon. And I'm thinking about it in the context of crowdsourcing. We heard about some crowdsourcing on Monday. We also had some discussions in between the breaks about Polymath. And I'm thinking about this because I want to try and understand the process by which mathematics happens and how you might build tools to better support that process. Now, I've come at that from being a mathematician. Once upon a time I was a group theorist, and then I also worked in computer algebra, and I worked in formal proof. And so I'm going to start with a little riff on formal proof, because formal proof is kind of what's driving this idea that you can build better tools to support mathematics. So I know some people in the room know about formal proof, or maybe they're the people who got here from Toronto yet. But who's actually, who was it I was talking to about homotopy type theory? Yeah, right. So some people have come across formal proof in that context. But for those who haven't, this is formal proof, but it is not, of course, a machine proof, because it's a page from Russell and Whitehead's Principia Mathematica, written in 1911. They set out to show that all of mathematics could be derived in formal logic by actually doing it. And of course doing it all by hand. This is page 79 of volume 2, from which you deduce several things. First of all, that Russell and Whitehead possibly had a sense of humour. The above proposition is occasionally useful. The above proposition being, that one I can't quite reach, of course I should have taken the pointer, 1 plus 1 equals 2. Now, why has it taken an enormous number of pages to get to that? Because we're deducing it using the axioms and rules that they set up way back at the beginning of volume 1. And so what this notation says is, well, the proposition follows from, oh, no, it's okay, I don't write it very much. Okay. I'm always scared I'll point them at somebody's eyes. So what this notation is saying is that this thing, 1 plus 1 equals something or other, applying 54.3, which is way up the top to something or other, yields 2, and so on and so forth. Well, the idea of computer proof, of course, is to get machines to produce that kind of stuff. And there's been a vast amount of work since the first experiments in the 1950s. And there are many approaches one can try. There are many ways of thinking about what the underlying formal logic is, of thinking about how much work the person does. So you can have it all the way from, essentially the person does all the work, the person just sits there and types this in, and the machine checks that they have actually applied the rules correctly. over to the machine having much more of a search procedure, many more high-level commands, so that lots and lots of stuff is generated automatically. And the reasons for the big investment, the big interest, has not been so much that this might be useful for mathematics. I mean, who's going to invest millions in computer proof for mathematics? It is because of its use in verifying computer software, particularly computer hardware. And without talking about it, in a great deal, I think if you're summarising where that endeavour has got to in 2015, well, I like to use this slide because people sometimes say, oh, well, computer proof is just, theoretical stuff of no use. This is the computer proof, the verification group at University College London. And the reason for using this slide is, well, they've got a terrifically big group, except as you see, none of them are ever there. One actually works for Microsoft, one works for Amazon, one works for Facebook, one works for Google, and this guy at the bottom has just come back from spending 2 years at Hewlett Packard. And there's real industry interest in this stuff for software verification. And the Amazon and Facebook guys are both really looking at verification of distributed systems. And this stuff is now embedded in the tool chain of software development. So the Facebook guys have started trying their stuff out on open source software just to find some bugs and show off a bit. But it's also been picked up by mathematicians, not by any means in an everyday sort of way, but essentially to prove that in principle you can show that in principle you can take a big mathematical proof and completely formalize it in this way. And the poster child for this is Tom Hales and his proof of the Kepler conjecture. The Kepler conjecture is the one that says if you want to pack a bunch of, well, in Kepler's case it was cannonballs, but here obviously they're tennis balls, what's the most efficient way of packing them so that the space in between them is as small as possible? And the answer is the most efficient way is the obvious way, this way, the way you would think. There isn't any other strange way of packing them all, which gives you a denser packing. And Hales proved this result, or submitted a proof to journals way back in the late 90s. But the journals published it with a caveat that they weren't really able to verify the numerical parts of the proof. The numerical part of the proof relies on an inequality between two numbers. So Hales, being that sort of a person, thought, right, I am going to go back and do all this numerical work inside a theorem proof and get a proof of what I want. And so I think one can say that is that it's a proof of concept. Large computer math proofs are feasible. If you want to take something or other, and do it in this computer proof style, you can, if you have enough time and enough resources. And there was certainly a lot of debate when computer proof started to emerge about whether it was acceptable or not. And I think the feeling is now, well, of course there's still debate about it, but you see leaders of the field now starting to accept it. So this is Tim Gower's blog, very influential Fields medalist. He's talking here about a different kind of computer proof. He's talking about using a SAT solver to find a counterexample to something or other. And what does he say down here at the bottom? He says, I personally am relaxed about huge computer proofs. It's conceivable that the authors made a mistake, but that's true of conventional proofs as well. And that's quite a statement of sort of shifting opinion about these things. At the risk of simplifying, this is not really what Thomas Kuhn said, but people like to say it's what Thomas Kuhn said. Is, what happens is, how the theories change, well, just all the old guys die off. Different generation. I know that's not what he really said. And of course, it's extremely hard work. Here you have from the Kepler conjecture, if you like, the credits rolling up at the end of the movie. An awful lot of people, they took about 10 years over it. If you look at in the middle here, you'll see a lot of names of Vietnamese extraction. And the reason for that is that to make his NSF dollars go further, he set up a team in Vietnam to work on this. He had a team of master's students and PhD students, and then a guy called Jonathan Adams, who must be on that cast list somewhere, whose job was to kind of project manage that aspect of it. Jonathan Adams is a project manager who, standard software project manager from a commercial company who has who happens to be interested in this sort of stuff. So it's a very different approach to doing mathematics. A similar endeavor was Georges Gontier of Microsoft, who produced a machine check proof in the Coq system of the White-Thompson theorem. The organization there, well, similarly, a lot of hard work, 6 years effort. That's rather different. He doesn't have a large cast in Vietnam with a project manager. He has a very small, tight team at Microsoft in Paris. But again, proof of concept. If you want to, you can automate one of these proofs, given sufficient time and resources. Well, I've been working in this area for quite a long time, and I could see all this was happening, but I was seeing also that in one sense these were remarkable achievements, but they weren't helping us actually create new proofs. In both White-Thompson and the Tom Hale's work, they both knew more or less what the proof was before they started, and then they were formalizing it in Coq, but they weren't having the new and creative ideas. Gontier did have that's more of a digression, but Gontier and co did come up with a different way of doing part of the stuff in the middle of the proof, but that wasn't a completely new approach. It was more a different way of engineering a lot of the technicalities of it. But it doesn't help you with this bigger question of, well, where do proofs come from anyway, and how do formal proofs fit into that process? And that's something. Well, you look. I must admit, I've got Cedric Villani's book. I've only read about 3 chapters of it, but that's something that people talk about from time to time, both in popular culture and in history of science. This is a paper by somebody called Debbie Wolf in Berlin, who was talking about, well, how complicated it was just to do these computer proofs, because you actually, if you're doing one of the computer proofs, it is a bit like playing a computer game. You sit there and you have false starts and dead ends and so on, and that's can be just as head banging as trying to do a proof on paper and trying to get it all out. So that's what motivated this project, and I'm going to talk a little bit about 4 themes related to my title, probably skipping over some of it if I get fierce looks from the chair where the audience, people want their coffee. So, supposing you want to understand where mathematical proofs come from. Well, here's a start at the top. I work in Oxford. I have the privilege of working inside the Andrew Wiles building. Oxford called their new math building the Andrew Wiles building. This is Andrew Wiles' proof of Fermat's theorem. Now, if you want to find out how that proof came about, well, of course, you could look at the paper, and looking at the paper would be just as opaque as any other pure math paper. In the Selma case, whatever that is, we make an analogous. Russell and Whitehead didn't deal with analogous. An analogous definition by replacing, and similarly, well, as we know, without understanding any of the details, we know that shorthand for, okay, I've done this argument in this case, if you understood that, then you can go away and figure it out in the other case. And if you didn't, well, just have faith or something. And I don't know. So, and this certainly is very hard to understand, and it certainly doesn't tell you where the proof came from. Indeed, you know, it was read before it was put on the archive and quite widely pored over before it was finally published. But people, you know, there were very few experts who really understood everything that was going on. It was more the case that, you know, once it was accepted by the referees, it was published, and between the referees and their conscience, what happened. Well, so if you want to find out what Andrew is up to, well, of course, you can go away and look at the vast piles of yellow pads in his office, or you can ask him. But of course, when you ask him, he will, you know, if you ask him, you'll ask him in a particular way, and he will answer according to the dynamic of the conversation. This is an extract from it was a National Geographic, I think, made a TV show about him. And there's quite a long interview with him that's very instructive to watch. Now, when people are talking about this interview, when people are talking about mathematics, of course they often focus on the creativity bit. Sometimes I realised that nothing had ever been done before was of any use. Then I had to find something completely new. It's a mystery where that comes from. And in the video, he sort of pauses. You know, this is obviously the moment that the producer, well, maybe the producer cut it to make it a more dramatic pause, but, you know, this is the production of the movie makes you think, oh, creative genius. But of course, as we all know, an awful lot of it isn't creativity. An awful lot is the paragraph before, for which one uses the highly technical term of slog. Well, I used to start trying to find patterns. I tried doing calculations. I tried to fit it in with some previous broad understanding. Sometimes that would involve looking at references, sometimes the modified things, etc., etc. So, you know, actually he was doing what any of the rest of us do when we're trying to solve a piece of mathematics. You know, we do some stuff and then we do some other stuff and maybe it doesn't work, or we phone a friend or go away and read something to see if we can get some inspiration. So, you know, there's a lot of other stuff going on that isn't the creative inspiration. Sorry, for some reason I just whizzed rapidly past the slide black joke because that shouldn't really be there, but I'll come back to that in a minute. I'm not sure if it's got moved or it's going to reappear again. So, what got me started on this was thinking about how do you understand what mathematicians do, and that also, or how do you understand mathematical practice in the jargon. Just as there's this new community emerging here at computational epistemology, there's a community emerging of people who study mathematical practice, driven by people like Brendan Lava, philosophers of mathematics, sociologists of science, actual mathematicians, educators. So when you start trying to understand mathematical practice, you realise, as we were discussing yesterday, you're moving off in the direction of interdisciplinary research, and you realise that there are many ways of going about this, and each approach has its own questions that it's trying to understand, its own knowledge, if you like, knowledge that's accredited by some sort of process or other. So, and its own methods of identifying questions, doing background work, deciding what counts as knowledge, writing it up, and so on. And well, because I happen to know various sociologists, I fell into this by talking to sociologists, and then I realised that even then there are different ways of doing things. There are people at the more ethnographic end of things who will embed themselves for a long time in mathematicians or whoever, and then write about what they see. Then a little bit further over on the spectrum, there might be people who are more informed by something like the human-computer interaction community, who might do that, but might want to start with specific research questions and only look for things that look as if they're answers to those research questions, which is a different way of doing things from just looking at, hanging out and seeing what we see. There are people who come from perhaps a more tradition of psychology who will want very precise hypotheses for which they can gather data, and of course that, and then run some numbers over them. Now that will means they can write papers with lots of statistics in, but it tends to rather restrict the questions they ask. They will be starting with very precise questions. They won't be hanging out with a bunch of mathematicians and seeing what they see. Does Andrew Wiles do more computational work on Fridays? Or something, I guess, at least slightly. And then people vary in, well, are they building a model of the process of how mathematics is done? And if you look at papers, particularly in areas like human-computer interaction, they always have a model with arrows and boxes and things. And it's really, and then of course we've done all that, you then want to place it in terms of the fundamental theories of the subject. And so your, let's say, social science PhD student, I'm consuming this stuff. I want to know what mathematicians do. Your social science PhD student is trying to write a thesis that places this in the context of various schools of thought of social science, or philosophy or anything else. They will be interested in being part of that kind of debate. Are they a Bruno Latour kind of person, or are they more a Barnes person, or a Bloor? But these are sociologists of science. They will be much more interested in positioning themselves in that debate, and perhaps writing a paper, which is 15 pages of that debate, which is, what's the word I'm looking for? Somewhat opaque if you're not part of that game, and then it's a bit like turning to the end to see who did it in the detective story, and then only 4 pages of the actual data. What I want to know. And it became it all becomes a different and fascinating world. However, eventually you have to stop maundering around and do something. So the people I started working with were with somebody called Donald Mackenzie, who's based in Edinburgh. He comes something out of the school of the famous French sociologist called Bruno Latour, and you can tell me in the break what. But Latour in the, when was this published? 1990-ish, I think? Late 80s, yeah. But this became, what he did was he went and sat in a laboratory and started to look from an ethnographic perspective at what people were actually doing in a laboratory. Now he comes a bit from this postmodern anything goes kind of school, but nonetheless, if you just read it as the account of what's happening in a laboratory, he's drawing attention to all the things that go on in a laboratory besides creating hypotheses and then verifying them. And then he points out, it's not really what you might read in the 101 methodology of science textbook. It's not really that they all sit down in the lab on Monday morning and say, right guys, what's our hypothesis this week? What experiment should we do on Wednesday? It doesn't work like that. So he was starting off a tradition of this kind of ethnography. And Donald Mackenzie worked in this area, he's still around, works in this area, particularly looking at where mathematics meets contentious areas. In the 1980s, he was writing papers on nuclear weapons and studying people who were looking at mathematical models of nuclear weapons. Some of us were talking about this in the break, I think, and the fact that if you just relied on simulations, you were losing stuff. You were losing all the heft because you only could, somewhat like if you're just relying on models of the behavior of the British electorate, you're losing stuff. In the 90s, he turned himself to people who were trying to mechanize proof. And a very interesting book where he goes off and looks at people doing that kind of formal proof, people doing other kinds of experimental mathematics, attitudes to the computer group and four-color theorem, and so on. But one of the conclusions he comes to from this is that even if you are using a machine to do the proof, you can't throw away all the responsibility of the people. It's actually people who decide what to accept and what not to accept. You can't just pass all responsibility off onto the machine. Trust in the machine cannot entirely replace trust in the human collectivity. In a more recent piece of work, he and a student worked with mathematicians in Edinburgh, doing sorry, I'm going to go on a riff about participant observer, but hanging out with mathematicians in Edinburgh, looking to see what they actually did. And it's wonderful because you read this, it's very readable. He tends not to go for 15 pages of theory and 5 pages of observation. He tends to do it the other way round. But it's very readable because you look at it and you think, oh my goodness, bang to rights, he's got us. So he's working with a particular group of analysts and saying, well, they all turn up to the analysis seminar every Tuesday afternoon. Why? Because half of them don't understand the seminar. Why? Well, because they're building a community. What does it mean to be an analyst in Edinburgh? It means you go to the analysis seminar every Tuesday afternoon. It's very, you read it, you think, ow, yes, we don't want people to know that. But one of the things he also is pointing out, and that goes back to what Wiles was pointing, is the vast amount of effort that goes into just messing around, decoding, translating, and transmaterializing. Sorry about that. I'm not sure what that word means, actually. It's a good word. Transmaterializing official text, without which advanced mathematics could not proceed, through tentative remarks that try and produce new orders out of old ones, with a crucial stage of disorder in between. In other words, what's going on when you write on the board and mess around? Something's happening. You can't get rid of that stage of mess, of informal thought. And of course he's positioning that against this idea, well, if you can formalize everything, well, if you're formalizing everything, you're just pushing that mess and disorder somewhere back, else you're sitting there trying to do the formal proof on the machine, and you've actually got a whiteboard or a piece of paper where you're doodling and thinking. And this image, which I took at the Institut Henri Poincaré in Paris, where they have very big blackboards. This is a life-size Dan Grayson, half of Dan Grayson. The blackboards go way up to the ceiling. Now what he's actually doing is explaining his computer proofs as part of the homotopy type theory endeavour. Somebody said he was here giving a talk recently. It must have been one of the Toronto people. I mean, here in Canada, not here.
Sorry. Hales was here not 2 months ago.
Yeah. But you see what's happening here? Well, it's classical, elegant blackboard technique, and we have had a bit of rubbing out and messing around up there. But actually, what you've got right at the top is it's making this point about the use of theorem provers. He's actually explaining in that bit in the middle up at the top. Well, I'm using this version of Agda with these settings of the compiler, but somewhere else I'm using those settings of that, and because this didn't quite work, I'm having to use a specialist bit of code I wrote for the other thing. And so the point is, even in this area of formal proof, there's just as much sort of messing around and contingency and so on. And it also, you can then go off the whole other concept. Well, are formal proofs reproducible? Well, not unless you set up some, virtual machine in the cloud somewhere that will exactly replicate all of that stuff that he had in the middle of the top of the board there. We all know the thing of trying to resurrect stuff 2 years later and change to Emacs and change to the operating system, and it just wouldn't work. sorry, I sent it to Donald. I couldn't, the modern world. I took a picture, emailed it to Donald Mackenzie in the talk, and said, "Great, took a picture." So that's social scientists, and they're the people of that school. They're observing things and seeing what they see. They're positioning it against theories, which I don't particularly want to talk about. But they're not starting with hypotheses, and they're not really trying to build models of what's going on. I'm somewhat embarrassed to be sitting with, but you haven't disagreed with what I just said.
I don't think they haven't any hypotheses. They do have hypotheses.
We can talk about that in the break, yeah. But I suppose what they don't go in saying, I am going to test the hypothesis people always do algebra on Fridays, do they? They don't have those kinds of very tight hypotheses.
Yeah, I didn't agree.
So, this is a world of people. This is a world where you want to study mathematicians doing mathematics and see what happens. Now, the next element in the mix is the Polymath Project. You see, one thing about this, if you're doing this kind of ethnography, of hanging around mass common rooms watching mathematicians, well, it's quite hard work, and not every social scientist wants to do it. And there are many, many other things for smart social scientists to study, like why the British Labour Party has completely collapsed, for example, or why people lie to electoral polls, which seems to be the best hypothesis so far as to what they're not. I'm sorry, I don't know, I'm just reading the papers. But in recent years, there's been a new experiment led by the mathematicians themselves, the experiment that they call Polymath. Well, what's Polymath all about? My next slide is meant to be an example of Polymath. Where'd it go? There it is. What's Polymath all about? Well, just skipping the previous slides, Polymath is about a bunch of mathematicians collaborating, but instead of collaborating around a whiteboard or in a coffee room or on Skype, they're actually collaborating in public on a blog. And this is an example of what's going on. You can see in there, well, at least one name that probably many people recognize, Terry Tao, very eminent mathematician. What they're doing here is, you may have heard of the twin primes conjecture. The twin primes conjecture says that there are infinitely many prime pairs, like 3, 5, and 11, 13, and so on, 17, 19. There are infinitely many of these. Now, what a mathematician called Zhang did a very remarkable piece of work a couple of years ago, where he didn't prove the twin primes conjecture, but he proved the 70 million primes conjecture. What does that mean? Well, what that means is there are infinitely many pairs of primes such that the difference between them is less than 70 million. And of course, what that means is if you could get that bound down from 70 million to 2, you'd have proved the twin primes conjecture. And so what they're doing on this blog is trying to get that bound down. And by a collaborative process carefully organized by Terry Tao, they managed to get it down to, sorry, the jet lag's kicking in, I can't remember what they got it down to, 400 and something, 200 and something? 200-ish. That's right, I think it's on the next slide. What the number actually was. And the point about this is, well, several points about it. First of all, it's just a remarkable collaborative endeavor by the mathematicians led by Terry Tao. You know, it worked. But also that they were prepared to do all their work in public in this way. So, and you can see the kinds of things that are going on. So this is mostly, this slide is chosen by the, there's an awful lot of this material on the web, I chose this particular slide solely because it's sort of small enough to get several bits of conversation onto one slide, rather than as any particularly significant part of the proof. But you'll see, here's Isabel Harkos, he's messing around. He's saying, oh look, that's good, that stuff up there is a stronger statement than I had before. And then he's saying, oops, I made a mistake. I believe this is doable, but not really important to the project. So he's sort of, as one does, you know, he's thinking about something that might be doable, even if it's not quite what we want. And then, well, actually, this is where the efficiency of the blog shows up. Terry Tao, who's kind of choreographing it all, is saying, okay, well, that was a nice idea, Harkos, but actually, let's stop thinking about this alleyway. It's not quite going where we want. Try to move back onto the next one, and so then they go off and pursue a different idea on a different blog thread. And then a few hours later, Harkos comes back and says, oops, that was false. Which tells you, you know, look at this and draw all kinds of conclusions, but of course one conclusion you can start to draw is actually you have to be a certain kind of person to want to work in this way. You know, have everybody in the world, including a bunch of people in, you know, London, Ontario, on whatever day it is today, the 8th of May 2015, you know, look at what you did. Anyhow, they've actually done a number of these experiments, led by senior mathematicians like Tim Gowers, like Terry Powell. But of course, one of the things that these endeavours do, as well as actually proving the results, is they provide you with this new kind of mathematical object for study. The blog provides a record of all the discussions. And this is a paper written by Tim Gowers and Michael Nielsen shortly after the first such endeavour, which was published in Nature. And they're talking about the proof of something called the density-Hales-Hewitt theorem, different Hale. And they point out, you know, the importance of having this record of the discussion. Who would have guessed that the working record of a mathematical project would read like a thriller? Well, and so for that one they published it. Incidentally, they decided to publish under a nom de plume, DHJ Polymath. So the talk you're not getting is about the collaboration and Hardy and Wright's collaboration and this kind of collaboration and so on. But I thought the talk you're not getting is on the archive, but my collaborator is still messing with the images, so it will be on the archive in a day or two. They publish these things in the regular way, but to get around the fact that, of course, they've got a lot of authors, and in principle, anybody could join in on the blog and contribute. They just published under a nom de plume, which raises a whole bunch of other issues. You know, if you live in a jurisdiction that is bean counting its academics, well, what do you do about this person? DHJ Polymath, you know. Can DHJ Polymath get tenure? You know? And so on.
Teaching ratings might be good.
Yeah. So you have these polymath phenomena, and one of the things that's remarkable about them is that they're just organised by the math community themselves. You know, it'd be easy enough for us computer scientists to go away and say, right, we were all singing, all dancing, collaborative platform. And guess what? They wouldn't have used it. In fact, so they're just using a blog plus various social conventions. Be polite, make your comments easy to understand. It's okay to have tentative thoughts, and so on and so forth. And that, you know, that in itself is rather interesting that they did it this way. And there were various principles underlying this, one of which was accessibility to everyone. So at some point, somebody said to them, well, why don't you just use GitHub or something? And in particular, when they are, if you look at the part of the blog where they're actually collaborating on a blog to write the paper, it's just a complete pain. You know, somebody posts a list of corrections, and then just because, you know, everything gets muddled up and very hard to follow. And at that point, somebody said, well, look, couldn't we just shift all this Git to GitHub? We have a version control system, essentially. A distributed version control system, so you can keep track of all the changes much more easily. And Tao said no, because I want this to be accessible to everybody. And there are some people, some mathematicians for whom, you know, trying to get to grips with something like GitHub will just be a bridge too far. I don't know what his evidence was for that, but that's what he said. And so, you know, they didn't do GitHub, they weren't really complete. The homotopy type theory, of course, they are using, they seem to have got over this obstacle. I mean, I don't even know if it is an obstacle, you know, really, it's just Terry Tao. That's why it's interesting, you know, Terry Tao being a very influential person, his thoughts about this, I don't think they have much discussion about whether to use GitHub, it's just Terry said, no. Okay, so, well, so far I spent quite a bit of time talking about the background. What am I actually doing? Well, what we're actually doing is using these proofs to see what they tell us in general about the process of mathematical proof. We just started this project, but we've done one piece of work which I do want to talk about, was to look at not at the big Polymath projects, this thing, but at some other experiments they did called mini Polymath, where they were taking questions from the International Math Olympiad type questions. Now the big polymaths take, you know, several months a year to solve. These are new questions. These things are much shorter and typically take just a few hours to solve. But they were doing this just to play around with the format and see what would happen. And so Alison Pease and I looked at one of these mini polymath problems just to see what it was going on in each of these comments. What do mathematicians actually spend their time doing? You know, if you ask them, they will remember the bits that they want to tell you, but if you actually observe them, what do they spend their time doing? And, well, it really was quite interesting. We did this by, well, sorry, I won't tell you about the methodology for doing this classification, but there is a, you don't start with fixed categories. You start with informal categories and gradually refine them, and that's a method relating to what the social scientists call grounded theory. But what did we find? Well, of course, the goal of all this is to get to a proof, and you might think that most of this stuff was proof steps. I don't know. A implies B, therefore. But actually, when you look, of course, a lot of it isn't proof steps. So, I mean, what's this one at the bottom? Oh, yes, it does seem so. And yes, I'm not sure it would help either. Well, that's clearly not a proof step. It's, what is it? It's a bit of chat. But it's serving a purpose. It's keeping the conversation going. So, it's reassuring the person before that, so, what's this thing above? Somebody's believing something. The thing above, they're talking about counterexamples. I sort of, you could go off into a riff about Lakatos here, what we do in the paper, but I'll leave that one. So, what are they spending their time doing? Well, only 14% or so is actual proof steps. What's all the rest of it? Well, about 20% is conjectures. And you saw on the previous slide a conjecture. People are playing around with conjectures about what might be true, what might work. 10% is playing around with concepts, and I haven't told you what particular example we were looking at was, but the way it's phrased is a way in which it's possible to immediately go down, it's possible to immediately misunderstand the question. And a lot of people do immediately misunderstand the question because they misinterpret the concept of the vulnerability concept of Python. So, and what's this? 33%. Well, 33% is playing with examples. That goes with conjectures. That's, you know, somebody, we're trying to figure out what's going on here, so let's play with an example. Again, that's, you wanted to talk about that. 23% is other. Well, what's other? Well, all sorts of things. Some of other is these social moves in here. You know, I'm not sure it would help either. That sort of thing. People reinforcing other people's statements, and so on. People correcting other people's statements. And so that was really quite surprising. And we spent we then in the rest of the paper, because given the motivation is to think about, you know, computer support for these sorts of things. Well, we're quite good at computer support for proof. You know, we spend a lot of time thinking about that. But computer support for some of this other stuff, much less good at. Computer support, I mean, you might say, well, we only want computer support for the boring bits, you know, the conjectures and the concepts and the fun bits. But it is quite striking that in that we've I could have had computer algebra computation as a separate category. That would be in, where would that be? That would be lurking in the 33%. But that there are some things that we've given far less attention to. I think as time is running short, I won't tell you about the other example, which is analysing math overflow questions. But I will tell you about the other bit of this thing was, I was using this strange phrase in this title, social machines. Now, I said earlier on that, you know, social scientists, people vary as to whether, when they study a phenomenon like this, they want to produce a model with boxes and arrows of what's going on or not. Well, the context in which I'm doing this work, well, let's face it, the money, the grant, comes from a big program around this new term called social machines. This was a phrase coined by Tim Berners-Lee, who was thinking about an overarching way of how people and machines combine. Now, many people have thought about that and come up with an enormous number of different terms for describing things like networks of services or agent-based systems or human computation or whatever. Social machine is, social machine is one particular thing, and it's a rather vague and generic term compared with some of the much more precise things going on in some of those other areas. But the definition used by the team is purposeful human interaction on the web, which could be anything, you know. It could be buying something on Amazon, it could be taking part in Polymath, it could be sending obnoxious tweets to people. But then it's to try and think about the overall issues that pertain when you're doing that. So things like designing social computation. So these interactions to do the polymath proofs. Well, they're designed in this rather informal way by having rules of engagement about what you can do. And they're also, if you include that as part of the design, what is the role of the moderators? I haven't talked about that very much. But, there's accessing data and information. Now, the way polymath is done, they don't have any rigorous way of doing external calls to things, although in this twin primes thing, there's one place where they are doing some computation, and it's actually, for the computer algebra or numerics expert, many computer algebra experts in the room, it's really very amusing to look at it, because what you have is a famous mathematician saying, well, I've never used Mathematica before, but I just took this script and fiddled a few numbers, and I came out with the number 87. And then B famous mathematician says, oh, I got one of my students to try it in Maple, but he came out with 4. And C, famous mathematician, says, oh well, you know, let's leave that for the moment. And they're playing. It's you know, you can have a whole thing about, you know, how groups of people take more risks. You know, a group of people crossing the road will take more risks than an individual crossing the road. This group of people will sort of play fast and loose with these computations. And you want to scream, no, it's not as easy as that. But you know, then also, you know, who would be brave enough to tell Terry Tao that he was being, you know, somewhat rash in his use of Mathematica? There's a whole things of accountability, provenance, and trust. Now, this is a very specialist community of people who, although some of them use false names or use doing it anonymously, you know, everybody kind of knows who everybody else is. You know, what would happen if somebody tried to pretended to be Terry Tao? Well, it would be really difficult to pretend to be Terry Tao in a way that would hold credence for very long, wouldn't it? For people who are fans of British detective stories, there's a detective story writer, Dorothy Sayers, who had a sort of posh English lord called Lord Peter Wimsey, who was a detective. And there's some crucial scene where somebody is pretending to be Lord Peter Wimsey. If anyone's read this one. And he's found out by a very French thing, a wine tasting. Because the true Peter Wimsey is a so it's a bit like this, you know. You couldn't really pretend very successfully to be Terry Tao for terribly long. And there are whole sort of issues of governance and finance and management. Now that you know, that's a broad framework for looking at these social machines. When you look at polymaths within this, some of these, you know, don't become particularly relevant. It gives a way to think about it, but it also gives a way to think about, you know, broader questions about computer proof or future models of mathematical publication or whatever it might be. So, skipping past. Sorry, I've left this out, but the online encyclopedia of integer sequences is a social machine. Discuss. Right. You know, what if you've got future models of mathematical publication? Where does all this stuff sit? Where does computer proof sit? Where does discussion on blogs sit? Are we still going to be writing papers, etc., etc.? My group are doing at the moment. We've just we've got a couple of new people joining the team in August. What we're doing is we're continuing this kind of ethnography. We're doing ethnography online collaboration. We're also doing some ethnography at the Newton Institute, which is a bit like Fields Institute. It's a place where mathematicians come together for specialist workshops and so on. And we're having an interesting discussion with them. They want to know, they're thinking about how you might have a hybrid model where you sort of augment coming together at research institutes by web-based collaboration of some kind. Although they're being rather careful about this because they don't want the funders to say, oh, well, wait a minute, you can do all this on the web. You don't need funding to invite people to Cambridge. We are trying to model what's going on. In the slide with the pie chart, I was just looking at, you know, tagging what was going on. But can you actually model what's going on? There's a lot more in there than a formal proof. What kinds of logical frameworks might you use? And there's a whole endeavour called argumentation theory, modelling patterns of argument, which might be one way of doing it, because you're trying to model. You see, not just A implies B, B implies C, therefore A implies C, but also, well, I think A might be true, but here's some evidence why it might not be. You know, you're trying to model much more subtle things. And then we're also thinking about how you would actually, not so much how you build a polymath type thing incorporating a theorem prover, but just what will be involved in doing so. Right, yes, I've got 5 more minutes and I'm going to tell you about Ada Lovelace very quickly. What is this? Well, apart from being a piece of, it's something from the Bodleian Library in about 1827. What is it? Somebody with beautifully legible handwriting, which is always nice in a student. I had not, till Mamma showed me, understood the sums where both multiplication and addition signs were used, in consequence of which the former examples must have been wrong, as I thought they were as follows: 5 times t equals 10, to which add 3 equals 13, multiplied by 4 equals 52, instead of 5 times 2 equals 10, to which add 3 times 4 equals 12. So, who is this person and who is her mother? Well, the person is Ada Lovelace, and she is figuring out the difference between 5 times 2 plus 3 times 10 and 5 times 2 plus 3 times 10. Ada Lovelace continued her interest in mathematics and went on to write a very important paper, prescient paper about Charles Babbage's analytical engine, which was a design for a computer that was never built. Ada Lovelace was born in 1815, so she was about 12 when she was doing this. In Oxford, we have a wonderful archive of her correspondence from which this came. Oxford is organising her 200th birthday party. Being female, you see, she had no university home to organise her 200th birthday party. Boole is also 200 this year, but Boole came from Cork. So the University of Cork is devoting itself to Boole's 200th birthday. We're doing Ada's 200th birthday. You can come to an exhibition where you can see this and various other amazing things. And you can come to a symposium on the 9th and 10th of December 2015. Or you can watch it live streamed, we think. Once we've sorted out some incredibly complicated internal argument about invoicing for the live streaming. So that's it. That's me.
So we have time for one question, possibly 2.
Are there any interesting problems of mathematical physics and theoretical physics that are sort of coming into the Polymath Project?
I'm not aware of it. I think because the people driving it tend to be people like Bowers and Tao, who tend to be more, more pure mathematicians. I think and if you go and look at Gowers' blog, they have various discussions about other things to do by this approach. I think there's nothing to stop anybody running an experiment of this kind, but I think that particular crew haven't done that many because it is very time-consuming. When you look at, they wrote after the last one, they wrote a very nice survey article. Tau in particular, it's a vast amount of time.
You were mentioning about Cedric Villani. Was
Yes.
he doing on the Boltzmann theorem or Boltzmann equation? Was he working on that?
I'm sorry. I was mentioning Cedric Villani as a phenomenon. I don't know if I don't think he's involved with polymath, but he might be. I just don't know.
Last question.
Yeah, this was, there was a remark early in the talk that raised a question about the value of computer proofs. So partly if they're not really transparent, so you suggested that in some cases you don't actually learn a lot from them. And so I was wondering, there seems like in some cases proofs that are instructive, and I wonder if there's a general worry about formalized proofs or computer proofs that they aren't as revealing or heuristically valuable as...
Well, I think that argument has been put forward, but then on the other hand, there are other arguments to set against that. So, for example, this question of, once you've done the computer proof, supposing, as I was saying, supposing you can set up a suitable virtual machine and keep the whole thing going, it's done. You've got a proof. You've got an enduring object, which is the proof. Where if you look at paper proofs, there's a very interesting paper by somebody called Alma Spinder. She's in philosophy. And she's looking at the paper proof, the classification of finite simple groups, and pointing out that actually, I know that's a vast amount of, it's a very, very big piece of mathematics of many thousands of people, that it relies on a lot of technical tricks, and it relies on, it's quite difficult to understand the papers, and if a mistake is found, then, well, hopefully there are enough people around to understand it to fix the bug. And she's making the point, actually, wait 50 years, all those people will be gone. There isn't an army of people working on the classification of finite simple groups anymore, but the problem is solved. So, these things will have an archival value or longevity. There are a number of different things you can set against each other. But I think also you can say, in response to your, it's a balance. You might want to have the principles set out, which you can have in a textual way or an annotated way, but then once you dive down into the gory detail, these days if you ask Maple to do a complicated integral for you, you'd have to be a real glutton for punishment to go back and look at, the actual. So it's sort of levels of trust in the community. The consensus around what's boring and going to be hidden and what's a valuable part of the argument and needs to be kept.
Okay, the real last question from
It's just a comment. I think the applied math analog to the Polymath Project goes by a different name. It's called the IPCC. Different scale.
Yeah.
That's it.
Thank you very much.